So this may actually have some kind of weird effect that I'm not planning on. Oh, can do that. I decided I don't want to try using that computer and this computer together again, but I think as long as I stick to this computer, I'll be okay. All right, so normally in the past, I'd walk around and I'd look at all your answers, but I think today I'm just going to kind of put my answer up here. Hopefully some of you got it right. Usually most people don't have this one right, so don't worry about it if you don't. And I'm just going to have you help me think through this. And what I recommend is, that's my velocity graph. This is going to be my position graph. I'm not going to put any units on it. I can have my time axis there. This is time. And it helps me if I divide this up into a few different parts, because crucial things are happening right at these times. Okay, so in the beginning, velocity is positive. Is it, so if I were doing this, if this were my velocity, what would I be doing? How would I be walking? I'd be speeding up, slowing down, walking at the same pace? Same pace. So this is the same pace, and is it forward or backward? Here's zero velocity, negative velocity, positive velocity. By just sort of, by definition, we call positive forward and negative backward. So this would be like me walking from left to right, generally, at the same pace. So if remember that this, what we're seeing here, at any given point, that value is the slope of the position graph. We've been going from position graphs to velocity graphs. This is making you go backward. So what this tells me is that the slope of this graph needs to be positive and the same the whole way. So I'm going to draw a line here, a positive slope, and is it going to be curved or straight? Straight. And we don't have enough information here to know what the starting position is. I can pick any point for a starting position I want. And really, we don't have any numbers either. So what this slope is doesn't really matter. I'm just going to randomly pick that. I'm going to say whatever the position is, I don't know. But I've got a positive slope, and it's a constant slope. So I'm adding on, with every second, I'm adding on the same number of meters. So I've got constant positive velocity corresponding to a constant positive slope. So now this is going down. Does anybody out here have any ideas what this is going to look like here before I give you hints? You think it'll be like that? Yeah. So right here, is this value positive or negative? Positive, which means in this area, the slope of this line still needs to be positive. And here, the velocity is still positive, so the slope is still going to be positive. But that value is decreasing. So what this is showing, since velocity is positive and getting smaller, this slope needs to be positive but getting smaller. And right here, what's the slope going to be on the position graph? If you're at zero velocity, how much is your position changing? How fast is it changing? It's not changing at all. So what's the slope going to look like down here when I get to this dotted line? It should be flat. So we've got a straight increasing region where we have constant positive velocity. Then we have sort of this downward curve. I think of it as a downward curve. And then it should be level right there. And now the slope of this needs to do what these values are doing. So the slope of it is 0 right here. And the slope is going to become negative and then get more negative and more negative and more negative and more negative until right there. So it's going to keep curving down, 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 down until right there. And then what does it do? Anyone?
The curve back up.
Curves back up, yeah. So here we've got So the velocity represents the slope of the position graph at any point in time. So we've got the most negative slope on this graph that we're going to have. And now we're still going to have a negative slope down here. But that negative slope is going to get smaller and smaller and smaller until right there when the slope here becomes 0. So it's basically going to do, it's going to do kind of the reverse of what it did earlier. Just like that. So the steepest negative slope is right here. And then it's still negative, but it's getting less steep until you get right there. And then velocity is 0, so there's no slope. And now, what do we do after this?
Draw a straight line.
Straight line, yeah. So velocity is 0 all along here, so there's no slope from then on out. So if you were to just stand in front of the motion detector and try walking like this, you'd walk away from it at a sort of relatively fast constant rate, and then you start to slow down, and then you wouldn't really come to a stop and wait there. You'd just slow down, and then you'd be going backward, and then you go backward faster and faster, keep going backward slower and slower until you eventually stop. So tricky stuff. The homework is going to be like this, except we're going to throw acceleration graphs in. Does anybody have any questions about this? Okay. So I've been getting some questions about the homework. First, I apologize for the default point value for practice that the school set up was 10 points. And I usually put in 5 points for homework. So put in a 5 for everybody, and you all got 50%, and then you got an F. So I was amazed that I think 6 or 7 of you immediately emailed me, and I fixed it. Hopefully I won't do that too much, but I screw up a lot. You've seen that already. Let's see. Let me just kind of go through this. So the first, if anybody watched the motion matching video relating to that first homework where I said, I'm not really going to go over this. If you need help, watch the video and then we'll talk about it later. We can talk about that now if you want to. I want to go over the homework kind of briefly and see if anybody has questions about that. I don't think I'm going to do this slideshow. My classes have been going too long, my live sessions, so I'm going to try to keep this one short today. So we're going to get to the acceleration notes, and then we're going to be done. And the rest of the people here, hopefully we'll just have some chill time when we're done, because I feel like I've been running hectically around, and I don't know, you're probably all relaxed, but I would just think that I would bother you running around like I've been doing. So I'm going to try to chill myself. All right, let me go back to this, and then I'm going to fish around in my notebook and get out my answer keys. And I know all of you need this. I'm not going to give you the answer key, but you can print it out. First, this was the first homework. Move that over. So this is the thing that I said if anybody still has questions about, we can talk about. But everything else you're going to need is in this packet. And right now I'm kind of thinking this will take us about 2 weeks to get through. Oh, you got one? Great. You're welcome. You're welcome. You're welcome. This class is always so polite. I get to hear and it's funny. Okay, it's funny because those people say thank you, and I'll say you're welcome, thank you, you're welcome. And then when I get to over here, people are so polite, they're starting to think, I bet he's sick of saying you're welcome. And then they get really stressed out about whether they should even say thank you. But that's a good problem to have. So, any questions about this from the first day? And so people at home, can you hear me still? Are you alive? Can somebody make some noise?
Yeah, we can hear you.
Okay, all right, good. And if you can't see something, or you have questions, just jump right in.
Yes, sir.
Well done. So this was last night's thing. I'll just go over the answers really quick in case somebody didn't do this. I vaguely remember screwing this up at some point, so these answers may be wrong. I have a memory that I somehow messed up here and did the wrong part. Oh yeah, see here it is. I ask you to do segment A, and then devilishly I ask you to do segment D right after that. I don't know why I did that, and I'm really sorry. So is this the
second one is done for section B?
That's what it was. So I did B. So really quickly, if I had done D, the displacement would have been -2 meters, and the time would have been 4 seconds, and therefore the average velocity would have been -2/4, which is -0.5 meters per second. The distance traveled would have been 2 meters, and the position at the end would have been 0 meters. Did I get them right? Yeah, okay, all right. So I think I did this right. Can people confirm that? Yes? Yeah? No? Okay.
Yes.
All right,
Here.
so let's move on. Now, unless there are questions about that, we're moving to acceleration. And the acceleration notes are on...
Is this supposed to be on the screen?
I had the screen frozen. Sorry. Just let me know when I do things like that. I can see it here, I just didn't realize it wasn't there. Kind of looks like it should be brighter too, doesn't it? I'm going to see if I can brighten up the screen real quick. I'm just going to leave it. I'll move this down a little closer, if that'll help. So this is actually what I was working through the other day. It's my nice, neat copy. This is tonight's homework. These graph comparisons on this page and then on the back. So that's what we're doing next. All right, acceleration. And feel free to blurt things out. Usually I'm kind of, once I get to know you, I may call on people, but sometimes I'll just ask people for an answer, and it goes a lot more smoothly if you just blurt stuff out. So blank tells you how much something's position changes during 1 second. So this is change in position over change in time. That is velocity. And if velocity tells you how much something's position changes every second, guess what tells you how much something's velocity changes every second? What? Acceleration. So that's what acceleration is. I just realized I don't know where my cheat sheet is. If I need to cheat and look up any answers, I'm just going to have to figure it out myself. So is acceleration vector or scalar? Can you have a direction? Can you accelerate to the left or to the right? Yeah, so it's a vector. Acceleration can happen in two different fundamental ways, and this is the favorite trick question of lots of physics teachers. They'll say something like, you're in a car, you keep the speedometer on 60 miles per hour, and you drive around a track in a circle, and the speedometer never changes from 60 miles per hour. What's happening to your speed and what's happening to your velocity? So first, what do you think's happening to speed if it always says 60? It's staying the same. How about velocity? Is your velocity changing?
Yes, because your position changes.
Well,
I'll take that it's a no.
No, I mean, everything you said is true, except maybe because of the because. I mean, your position's changing, and your acceleration or your velocity is changing, and I don't know. I'm not even sure you're wrong, but it wasn't the answer I was expecting. And the answer is velocity is both speed and direction. So if you have a different speed or direction or both, then you've accelerated. So there are two different ways for acceleration to happen. You can change your speed or you can change your direction. If you're going in a circle, you're changing direction. So change speed and change direction. So just as an example of that, if you think of an object orbiting the Earth, there are a few different ways to think about it. If I stand here and I throw a ball this way, it's going to go like that. And if we think about that on a flat surface, that's just kind of projectile motion. You know, I give it a velocity this way, gravity accelerates it that way, and it travels like this. But if I stand on the Earth and I throw it hard enough, it's going to do the same thing. But as it falls, it's just going to keep falling right around the Earth. And it is accelerating the whole time. If you drop something, it accelerates downward at 9.8 meters per second squared. And that's what it's doing as it goes around the Earth too. So there's acceleration even if it stays the same speed but changes direction. All right, negative acceleration, what's the common sense word for that? Begins with a D?
Deceleration.
Yeah, deceleration. All right. Common units for acceleration. So if velocity is meters per second and it's telling you how much your position, which is meters, changes every second, what do you think the units for acceleration are? What's changing every second with acceleration? It's not your position, it's your velocity. So it's going to be meters per second, which is the unit of velocity, per second. But we don't usually write it like that. You can write meters per second. Sometimes it's handy when you can't do a superscript. But usually we write it like this, meters per second squared. And if you're if you're typing it, you can do the caret, meters. Well, all right, moving on. Analogous relationship between velocity and acceleration. I feel like this is the kind of stuff that probably feels pretty easy, but you really need to have a good, deep understanding of it. Pam has a velocity of positive 6 meters per second. That means she travels 6 meters for every second that ticks by. So after 1 second, 6 meters. After 2 seconds, 12 meters. After 3 seconds, she has gone 18 meters. But she's always going 6 meters each second. Another way to say this is for each passing second, she adds 6 meters to her position. Analogously, if Pam's acceleration is 6 meters per second, that means for each second, what does she do? Instead of adding 6 meters to her position, what's she adding to what?
She's adding 6 meters to her velocity.
Close. 6, not meters to her velocity.
6 meters per second.
Yeah, people get tricked by that every year. And I have to apologize. I love trick questions. So if you fall into my trick question traps, don't worry, it's okay. She adds 6 meters per second to her velocity. So they're really similar kinds of things. Velocity is the change in position every second. Acceleration is the change in velocity every second. Velocity adds meters each second. Acceleration adds meters per second each second. The velocity is the slope of a position versus time graph. Here, is that an F-35 going over?
Oh yeah, that's probably me.
That's all right. It's not too loud. So velocity is the slope of what versus time? Oh, nope. This should say acceleration. Otherwise, that's the same thing over again. So acceleration is the slope of what? So if I have position, time, and I measure this slope gives me velocity. What kind of a graph is the slope going to be the acceleration. Not a position graph like this. Velocity over time. So if you look at a position graph, position is in meters and time is in seconds. So the slope is just the rise. If you start here and you go to there, it's the rise over the run. So it's the number of meters divided by the number of seconds. If you have a velocity versus time graph, then the slope of that, if you're going from changing from this time to this time, this is the number of meters per second that you're increasing, and this is the time interval over which you're doing it. So the slope of this one is meters per second, and the slope of this one equals meters per second squared. So super important. This is, I put this big star here. That is one of the biggest things in this unit. That's the thing you need to come back to tonight when you're trying to do these graphs, just the relationship between the slopes. The acceleration formula, well, the velocity formula, average velocity was change in velocity, or sorry, change in position over change in time. Gave it away. Guess what the formula for average acceleration is? What's divided by time here? Change in velocity. So it's the same thing, it's just change in velocity rather than change in position. Can I go to the next page? All right. We're almost done with the notes, and then some good practice. All right, these are super easy. These are just applications of the formula. Suppose your velocity is 2 meters per second. 1 second later, your velocity is 6 meters per second. So just to practice using my labels here, this would be V0, and this would be V. What's your average acceleration over the time period? So if you want a formula for it, we don't usually put a line over A for average acceleration. I'm going to be dropping that, but for now I'll do it. Is change in velocity over change in time. And doing it the really careful way, change in velocity is just going to be V final minus V initial over change in time. I'm not going to write these out, I'm just going to do those in my head. 6 minus 2 is 4 meters per second. And the change in time says 1 second later, so this is delta t. So 4 divided by 1 is 4, and meters per second divided by seconds is meters per second squared. So that's the average acceleration. Now it could be that the first tenth of a second you accelerated all the way almost to 6 meters per second, and then the next 9/10 of a second you accelerated the rest of the way, and your acceleration wasn't constant, but still this is what it would have been if it had been constant. That's the average. All right, one more practice. This is what your watch reads. 8:01, 32 seconds. Your velocity is 6 meters per second. Then at this time, your velocity is 2 meters per second. Same thing, this is just a little harder because we're not given a starting time of 0. So the change in velocity is going from 6 to 2. So what would the change in velocity be? -4 meters per second. And the time interval would be what? 8 seconds. So it's going to be negative 0.5 meters per second squared. All right, so that's really it for acceleration. Any questions about anything? Now we'll do a few of these examples, and then you can have time to work on the homework, which is tricky. A lot of people had trouble with it last year and the year before and the year before. And I made a video that I gave you that you can watch, but I made it 2 years ago, and I'm better at explaining things now, so it may not do it for you. All right, so here we have, it says D and T, V and T, A and T. This is the position versus time graph. And we have to take this and transfer it and show what the velocity of this object would look like over time. And then we're going to have to show what the acceleration would look like. But the key is that these values, every single value at every single second, gives us the slope of this. And every single value here at every second gives us the slope of that. If you can remember that and you can think forward and backward, you'll be fine. So looking at this, is the slope positive or negative?
Negative.
Negative. And is it getting more negative, or like is it becoming a higher negative number or a smaller negative number? Like, is this slope getting steeper or less steep? Less steep. So it's a negative slope, and it's becoming less steep until right here there's pretty much no slope. So I need to draw a velocity that is strongly negative in the beginning, like this time, and then getting less negative until somewhere around over here at 0. So like that. Whether it's exactly like that or it curves, we don't really know, but as long as you start out with a more negative number here, and then you stay with negative, but it's less negative, you wind up with something around 0 there, you got it. So now acceleration, if we're going from there to there, this graph, any of these points, we should be plotting the slope at these different times. So at the very beginning here, is the slope of this positive or negative? Positive. And how about here? Is the slope positive or negative? Positive. And is the positivity, is it getting more positive or less, or is it staying the same? It's about the same. So I just need a constant positive line like that. All right. I don't know if, I can't remember which is the hardest. I mean, going from this to the other two, or going from velocity to the other two, or acceleration. I kind of think acceleration's the easiest one, but I can't remember for sure. There are a lot of different ways to think about this. You could just kind of think, oh, if I were walking in front of the motion detector, I'd start walking toward it really fast, and then I'd slow down. So that means my velocity is negative and going to 0. And I'm yeah. Oh, I don't know. I don't know if that way helps, because that would be positive acceleration. And anyway, I think the slope method is best. Okay, so what do you want to do first? Do you want to go from here to acceleration, or here to position? Anybody care? I think the easier one, probably toward acceleration. So let's do that. We just do what we just did. We look at what this, I'm going to do a dotted line, and I'm just going to consider this part of the event first. So the slope of this is, how would you describe it? I'd say negative and constant, right? So this acceleration in the beginning needs to be negative and constant up to that point. And what's the slope of this?
0.
0, so there. And this is impossible. You can't, well, maybe you can do that. I don't know. This sharp corner kind of bothers me. Seems like that should be curvy. But anyway, so you accelerate negatively, like that would be accelerating toward the sensor, and then you just stop for the rest of the time. No acceleration. Oh, no, you don't stop. You stop accelerating. Are you still moving here? Yeah, yeah. Okay. So now we've got to go back. I think this is a little bit harder. I'm going to draw the dotted line again. And now we're thinking, okay, each of these points along here tells us the slope of this. So whatever I draw in this section, the slope of it has to be 0 at first, and then the slope has to be negative and bigger, and negative and bigger, and negative and bigger. So wherever I choose to start here, I could start anywhere I want. I need, wait, did I say the slope is negative to begin with? Well, is this negative? That's 0. So the slope needs to be 0 at first, and then it needs to start becoming negative and get more negative. So I need to start it out kind of straight. I could start it here or here or here. There's no way to know. So I'm just going to start it here. And then the slope needs to get negative and more negative. So it needs to be steepest when I get somewhere around here. And then this is a negative constant number, so I need to continue with a negative constant slope. It's the same slope that I just ended on, and it stays that way, so it just goes straight now. So I've got a downward curving part, and then I've got a straight part. Good? Okay. And this takes a lot of practice, so if it's tricky for you, that means that's good. Hopefully it's everything in here shouldn't be too easy. All right, so now we've got to go from the right all the way to the left. Same kind of thinking. I wonder, before I do the slope thing, let's just think about it. Positive acceleration and then sudden negative acceleration. So that would be, if I were doing that, I would start accelerating this way and then negative acceleration. Does that mean I suddenly go back? It would actually mean I would start going this way fast, but then I would slow down that way. And if I kept negatively accelerating, once I got to 0, then I would start coming back. So that's kind of what's going on. So we don't know in the beginning whether the velocity starts out positive or negative from this. All we know is that there's positive acceleration. So now the slope. This slope starts out positive and then stays positive, and it's the same positive slope. So wherever we start here, let's just start down here. Just needs to be a positive slope, and it needs to stay positive until this turning point where things change. And then right here, when we jump down there, what's the slope now of this graph if this is the acceleration? Positive or negative?
Negative.
Negative. And is that negative slope going to change here? No. So it's just negative, and it looks like it's just as positive here as it is there, so I'm going to make the slope the negative of this. So however steep that was going up, same steepness going down. And just intuitively now, if your velocity is going up and then your velocity goes down, what do you think the curves are going to look like here? Anytime you have a change in velocity over here, you're going to get a curve. Like in this one, right there we get a curve because here the velocity was changing. Here the velocity was changing, so we get a curve the whole time. So we're going to have some curves. Do you think this is going to represent an upward curve or a downward curve? Is it going to go like this, or is it going to go like that?
Upward.
We'll see. Let's check it out. So the way I've drawn this, I've started out with a positive or negative slope. Like when I start drawing this, this is a negative number. So should the slope here be positive or negative? Should be a negative slope. And do you want me to make this easier, or do you want me to keep it like this? Because I kind of made this hard. I don't know if anybody can foresee why it's hard. Here, I'm going to do another one down here that would be it's just as valid, except it's going to be easier. So if I had done this, that's going to make this one easier. I'll do this one first, and then I'll go back. So if you want to do what I'm doing, we get a little bit of extra practice. So the reason this is easier is because the velocity starts at 0, which means the slope here needs to start at what? 0. And then the velocity becomes more positive and more positive, so the slope of this needs to become more positive until this time right here. So the slope is going to do something like that. And then the slope of this needs to stay positive, but it's going to decrease, decrease, decrease until there's no slope again right there. So by the time I get to this point in time, this needs to be flat again. So it's going to be kind of like that. So I've got, just to recap, on the left, there's 0 velocity, so there's 0 slope here. Here the velocity starts to become positive and bigger. Here the slope is positive and bigger. here the velocity is at its peak, so the slope's at its peak and positive. Here the velocity is still positive, but it's shrinking, so the slope here is still positive and shrinking until finally velocity is 0, so the slope here is 0. This one, I'll do this one, but so here the velocity starts out negative, which means the slope needs to be negative to begin with. And when I get to about right there, then the velocity is 0, so the slope should be 0. And then when I get to here, so slope should be increasing until I get to there. And then slope is decreasing until it's 0 right here. And then slope becomes negative and getting bigger. So you can see how that complicates things. It adds on this little section here and a little section there. So if your brain hurts a bit when you do this, that's normal. And your homework is to do both sides of this. Feel free to lean on the answers. You can look up the answers, check them as you go. In fact, I would do that. Let me go to my website. And then I want to check in on my stream and see if we can have a freaky experience of looking at this a couple minutes ago. Right here, graph comparison solutions. These are all the answers. So that's what they should look like. And then also I think if you go to the Google Classroom, there's a video link there, so you can watch me actually going over this from a couple years ago. Let's see if I'm still streaming. I am? Somebody's checking on it? Or people at home? Did somebody say you are? Oh, you're watching it? Yeah, so here. Not exactly live. If you go to the